All right, gentlemen, let's talk about these orbital physics practice problems that were put out before your test. Some of you guys, actually many of you guys had problems with these on the actual test itself. So I'm going to use these three problems as a demo for you, and then you need to go back and make some adjustments to your test to earn some points back. All right, so let's take a look at the first one right here. It says a 16,000 kilogram satellite is orbiting at 580 kilometers above the Earth's surface. What is the potential energy of the satellite? They give us the radius of the Earth at 6.38 times 10 to the third kilometers, and the mass of the Earth at 5.98 times 10 to the 24th kilograms. So we have some formulas from our formula sheet right there. So we have K equals 1 half mv squared. That's our kinetic energy. U, which is our potential energy. Then we have E, which is our total energy. And then we have the universal gravitational constant. All right, so we obviously need U right here, which is negative gmm over r, where the capital G stands for the gravitational constant, the universal one. Capital M is the mass of the Earth. Lowercase m is the mass of the satellite, and r is the radius from the center of the Earth to the satellite. Or you could also, capital M could be the mass of any object that is being orbited, and lowercase m would be the mass of the object doing the orbiting, and then the r would always be the radius from the center of the object being orbited to the object orbiting. All right, one of the pieces I want to take a look at right here, which is important to us, some of you guys I think lost sight on here. The answer to this is actually going to be in joules, right? Because if we take a look at this situation here, we have this gravitational constant which says it's m cubed over kg times s squared, right? So that's at the top, and then if you think about it, we're going to divide it by the radius. Well, the radius can't be in kilometers, can't be in kilometers. It has to be in meters, right? So we're going to divide out a meter, and what is that going to yield us? A meter squared. And then also on top of that, we have a kilogram on the bottom, and then we have 2 kilograms up on the top because we're taking the masses multiplied together. So it's going to factor out and leave us with 1 kilogram on the top, and then we still have our second squared on the bottom. So ultimately, our answer is going to be in joules. So you need to make sure that's the critical piece right there. We have to be in meters, and I think that's where most of you messed up on this problem. So let's go ahead and take our values and put it in there. So we got our U, our potential energy, is equal to negative 6.67 times 10 to the 11th, or negative 11th, I'm sorry, times 5.98 times 10 to the 24th, which is the mass of the Earth, times 1.6 times 10 to the 4th, which is the mass of the satellite, 16,000 kilograms. We didn't have to do any conversions up there. But the bottom, we have to get our total radius here, which is from the center of the Earth, right here, 6.38 times 10 to the 6th, right? Because it was 6.38 times 10 to the third kilometers, but there's 1,000 meters in a kilometer, and we need this to be in meters, so it's going to become 10 to the 6th. So that's the radius of the Earth, but then we have to take the satellite, how high above the Earth it is. It's at 580 kilometers, so to express that in meters, we're going to multiply that by 1,000, so we're going to end up with 5.80 times 10 to the 5th. When we work all this out, we end up finding out that our potential energy is negative 9.1693333 times 10 to the 11th joules, right? And we're going to express that in scientific notation, so we get negative 9.17 times 10 to the 11th joules. So that is our potential energy right now for this satellite as it floats above the Earth right now. All right, so then the next problem that we have, we are now dealing with, it says we want the total energy of a 210,000 kilogram SpaceX capsule orbiting the Earth at 900 kilometers above the Earth's surface. Again, we got the radius of the Earth and the mass of the Earth, which is the same from before. And again, our answer is going to come out in joules. But to get our total energy, we need our potential energy, which is U, right? There's our U plus our K, which is our kinetic. So we can plug it into both of these equations, add them together, and get our total energy. But if you remember from the video presentation I put out there on this physics last week, there's actually a shortcut way to do this, and it's negative gmm over 2r. So it's, again, the gravitational constant, the mass of the object being orbited, the mass of the object orbiting, divided by the double of the radius of those two objects together. All right, so here we go again. We're going to take a look at this one now. So we got our gravitational constant, we got a mass of our Earth, we got the mass of the object right there, 210,000, which is 2.10 times 10 to the 5th. And then we're going to double the radius of the Earth, again, it has to be in meters, so 6.38 times 10 to the sixth instead of the third. And then the orbit itself is at 900 kilometers, so it'd be 9.00 times 10 to the fifth to get it in meters, right? We're going to multiply it out by three more zeros there, three more decimal places. So when you punch this in your calculator, the other place that I am seeing some problems here is that when you put it in your calculator, if you're going to punch this whole thing in your calculator, make sure you put parentheses around this whole bottom piece. Otherwise, you're going to divide out the 2, and then you're going to end up multiplying this piece against the whole thing. So that can cause some problems for you guys as well. So when you do that, you end up finding out that the total energy of this guy is negative 5.752875 times 10 to the 12th joules, which ends up becoming negative 5.75 times 10 to the 12th joules. Oh, I didn't mean to put that. I'm sorry. That was a mess up right there. Oh yeah, that was right. I'm sorry. I'm thinking of something else. Anyway, so that's what we get is negative 5.75 times 10 to the 12th joules is our total energy now for this capsule floating around the Earth at the time. All right, so then the next thing that leads us to is our last problem. So now we have a research satellite. It's a 16,000 kilogram one that is orbiting planet Dagon at an altitude of 650 kilometers. The researchers want their satellite to be at an altitude of 800 kilometers to take some specific pictures. How much energy is needed for this orbit change? So I need to be able to change orbits, right? So if I know the total energy of the satellite at 650 kilometers, and I know the total energy of the satellite at 800 kilometers, can I just get the difference? And that's going to tell me what that energy change is that I need to boost this thing. So we're going to go ahead and work through the first problem here. So we have, actually let's go ahead and we'll pull it in from this direction. All right, so we're going to take our total energy, right? So 6.67 times 10 to the negative 11th, but this time this planet has 3.74 times 10 to the 21 mass, and our mass of our satellite is 1.60 times 10 to the fourth, okay, in kilograms. Our radius of our planet is 5.4 times 10 to the sixth. Again, it has to be in meters, not kilometers, so I'm going to change that. And then 6.5 times 10 to the fifth, right? So my altitude was 650 kilometers, so I need that to be in meters as well. When we divide that out, we end up with negative 3.2986118.2, and that just turns into negative 3.30 times 10 to the eighth in joules. All right, so then that becomes our energy for the planet for the first our total energy for the first one. For our second one now, we're just going to keep the equation the same, but the only thing we're going to change is this piece right here, the 6.5 just becomes 8.0. And we're going to go ahead and crunch those numbers. We get negative 321881290.3 joules, which turns into negative 3.22 times 10 to the eighth joules. Now, if we use it in the decimal form, we take these two numbers and we're going to subtract them, right? So you're going to take the bigger number, which is the second one. It's the higher altitude. It has more potential energy. So this guy has a higher number, even though it doesn't look like it. 3.21, negative 321 is definitely bigger than negative 329. We're going to subtract those. That's going to turn these guys to positive, and it's going to yield 798 or 7980527.86 joules, which is 7.98 times 10 to the 6 joules. And then if we did it the other way, just using the scientific notation, we're going to lose a little bit of the precision on that way, right? So we're going to subtract the two, and you're going to end up with 8.00 times 10 to the 6 joules. Neither one of those answers would be acceptable for me. But again, you can see that is the energy that it's going to take for us to boost this guy from one orbit to another. All right, so now if you have some problems on your test that you have not contested and you want to do, I would watch this video and go back and contest your problems and get some points back. The other one is if you have some problems that you haven't done. If you go back and redo these problems based off of what we have here, I will give you half the points back on those problems. All right, guys, I hope this is helpful. You have a great day.